Alright, hello class. In this video we are moving into the final module that this class will cover. And that's all about vector fields. Alright, so vector fields finally get us to that scenario where we are examining structures where we have multiple independent variables and dependent variables. Alright, so what is a vector field? Well, a vector field is actually, it's really just a vector valued function, which doesn't sound all that new. However, it is a multiple dimensioned vector valued function. So a vector field is a vector valued function, okay, with multiple independent variables. So what I mean by that is you could think of the vector field capital F of xy is going to be the vector, so this is a vector valued function of, we'll say little f of xy, comma little g of xy. Okay, so it's essentially a vector valued function that instead of the functions being in terms of t, they're in terms of x and y. And this is kind of tough to wrap our heads around. We can also have a three-dimensional version of it, or we have f of x, y, z is a vector valued function, little f of x, y, z, little g of x, y, z, and a little h of x, y, z. Okay. All right, so what this brings us to is vector fields are this situation where we have, say, 2 to 3 dependent variables and 2 to 3 independent variables. All right, so this is really an interesting module because what happens is we are taking everything we've done so far and bridging it together. Okay, so here's what's confusing though, or what I think some people will find confusing, is that as you can see, our independent variables and our dependent variables are both x, y, and z. Right? Our independent variables are x and y and z when it comes up. And our dependent variables are also x, y, and z. And this is where notation becomes a really important construct here, because what a vector field does, okay, is it takes a point x, y, z. Okay, this is a point, and spits out a vector x, y, z. Okay, and really, well, I'll just put it x, y, z, and I'll make it x bar, y bar, z bar, just to distinguish them. But what f does is it takes a point and gives us a vector. So essentially, for each point, okay, so for each point plugged into capital F outputs a unique vector. Okay, so how we visualize this is like this. Okay, so I'm going to show it in comparison to what we've seen before. So originally, our vector valued functions, so this was just our VVFs, right, which at each particular t, it gave us a vector, and we thought about those as vectors in standard position, right? So this could be, say, r of 0, r of 1, r of 2. Okay, so this would be r of t equals some function of t, comma, some other function of t. Okay, so this made curves in space. On the other hand, what a vector field does, okay, a vector field, instead of all of the vectors being originating at the origin, a vector field gives us a unique vector at each point. So we could have the point at the origin at 0, 1, at 1, 1, at, sorry, that's 1, 0. This is 0, 1. Negative 1, 1. Negative 1, 0. Let's say negative 1, negative 1. 0, negative 1, and 1, negative 1. Now what a vector field does is, if we're just looking at these points, and we can look at a lot more, we could also look at, say, negative 2, 0. But at each one of these points, what f gives us, capital F, is a unique vector. So we might have a vector here. That would be f of 0, 0. We might have a vector here. That would be f of 1, 1. Maybe we have a vector here. That would be f of 1, 0. Maybe this would be f at 1, negative 1. And so on. And what ends up happening is at each point, capital F gives us a vector. Okay, so, and that's why it's called a vector field, because when we graph this on a grid, it actually creates a field of vectors. And that is given by a function g of, whoops, not g, but little f of xy, and little g of xy. Okay, because each one of these at each point gives us a, say, different value. All right, so let's look at a really simple example to start with. Let's say we have the vector field xy, f of xy is equal to the vector xy. So this is, we could call this the identity vector field. Basically, it takes every point, and at each point makes the corresponding vector that matches that point. So what we would do is, I like to make a 1-by-1 grid to start with. All right, so here I've made a 1-by-1 grid going from negative 1 to 1 on both axes, and I've set up the points for that. Now we're just going to go through them and see what vectors we get, and in this case it shouldn't be that difficult. For 0, 0, we're going to get the vector 0, 0. Well, the vector 0, 0 doesn't do anything, that's just a point. Then at the point 1, 0, we're going to get the vector 1, 0. So that means this vector goes out 1 in the x direction and up and down 0. So at the point 1, 1, so here's the point 1, sorry, not 1, 1, but 1, 0, it's going to move 1 in the x direction and 0 in the y. So there's f of 1, 0, which is the vector 1, 0. But the trick is that these aren't all centered at the origin, but they start at whatever point we're plugging in. Okay? So at the point 1, 1, we get the vector 1, 1. So the vector should go over 1 and up 1. All right, so here's the vector 1, 1. When we plug in 0, 1, we should get the vector 0, 1. So that means we go left or right 0, but we go up 1. So this vector goes up 1. All right, so there's the vector 0, 1. And if we were to fill these out, again, this one isn't that bad. We'll get the following table of vectors here. So at the point -1, 1, we'll get a vector that goes in the negative direction 1, but up 1. Right? So here's -1, 1. Here's -1, 0. Okay, -1, -1. 0, -1. And 1, -1. Okay, because from this point on we go over 1 and down 1. Okay, and this is how a vector field is graphed. Of course, this does take a little while to do. However, I do want to show you how you do this by hand to get a sense of how this vector field is behaving. And if you think about what happens at, say, the point, this would be, say, -2, -2. Well, you'll get the vector -2, -2. At the point -2, 0, you get a vector like that. So I like to call this the explosion vector field, because what happens is that at all points, they're all exploding away from the origin. And the further they get away from the origin, the higher their magnitudes get. Now, in general, we won't be graphing these by hand. I mean, if I ever want to know what a vector field kind of looks like, I'll graph it in a -1 to 1 grid, or maybe a -2 to 2 grid. But that's not always practical. So what we'll tend to do is just use software. Now, before we say do that, let's actually see how we would do this with something a little more complicated. All right, so for this example, let's go ahead and just start taking a look at a graph. We're looking at capital F of xy is equal to the vector y comma -x. So this is actually going to be flipping some things around. So at 0, 0, we still get the vector 0, 0. Okay. But now at the point 1, 0, right, at 1, 0, this vector field flips x and y around and then negates x. So we're actually going to start by flipping. So y is 0 here, x is 1, so we'll actually get the vector 0, -1. So we'll go out left or right 0, and we'll go down 1. Okay, so this vector is doing this. So here's the vector 0, -1. Okay. Here, when we look at the point 1, 1, well, again, that flips and negates the x-coordinate, so it's the vector 1, -1. So we go out 1 and down 1. Okay, so out 1, down 1. Okay, then when we plug in, say, 1 or 0, 1, well, again, we flip, so we'll get 1, and then -0, which will just be 0. So we get 1, 0, so we get this vector here. Okay, and if we continue this on, we'll get a vector field that looks something like this. Okay, so it looks like these vectors are revolving around the origin, okay, in this case counterclockwise, or no, clockwise, so in the negative direction. All right, let's look at another example. Okay, so for this vector field, we'll take a look at capital F of xy equals the vector x minus y, comma 1 plus y minus x. All right, so let's take a look at what we got here. When we plug in the point 0, 0, we'll get 0 here for x and y, and 0 here for x and y, so we'll get the vector 0, 1. So we're not going out at all, left or right, but we're going up 1. So we get this vector here. Okay, and remember, 0, 0 tells us at what point it is we're talking about. So here's 0, 1. When we plug in 1, 0, all right, in this case, I'm going to plug 1 in for x, 0 in for y. So here I'll get 1 minus 0, and here I'll get 1 plus 0 minus 1. So this is the vector 1, 0. So 1, 0 goes out to the right 1 and doesn't move up and down at all. So it will look something like this. All right, then when we plug in 1, 1, well, 1 and 1 here for x and y, that will give us 0. And then 1 and 1 here gives us 0 again, but with the plus 1. So now we have the vector 0, 1. So it goes left and right 0, but up 1. Okay. Then let's do this next point, 1 or 0 comma 1. Well, 0 comma 1 is 0 for x, well that's 0, 1 for y, that will be negative 1 here. And then here, putting in 0 for x and 1 for y, we'll get 2. So we now have a vector that points 1 in the negative x direction and goes up 2. So it'll go 1 this way in the x direction and up 2. So fairly steep here. Okay, let me try that again. All right, that's better. Okay, when we put in the point here will be negative 1, 1. All right, so negative 1, 1. So negative 1 for x, 1 for y. That gives us negative 2. And here I'm putting 1 in for y and negative 1 in for x. We'll get 1 plus 1, so that's a 3 there. So at this point, we'll get negative 2 and then up 3. So it's even steeper than this last one we drew. And we go along this path, so, right, f of negative 1, 0, that will be negative 1 in the first coordinate, or yeah, first component, and 1, that'll be plus 0 minus a negative 1, so that will be 2 again. So we have another negative 1, 2, so that should match this one. Right, here's negative 1, 2, negative 1, 2. All right, and I'll go ahead and do the next 3. Negative 1, negative 1. Here we'll get a negative 1 minus a negative 1, so that should come out to be 0 in the first coordinate. And then here I'll have negative 1 plus a negative 1. That will also be another 0, so we get 0, 1. Okay. And then here at f of, that will be 0, negative 1. 0 is x, negative 1 is our y. So in that first component, we should get a positive 1. And in the second component, we should get, it looks like a 0, because that will be 1 plus negative 1 minus 0. So we should get 1, 0. Okay, so that matches with that one. So it looks like to me the pattern is, it looks like along diagonals we're getting the same vector out. Okay, so this doesn't seem to be along a diagonal we've already seen, so let's see what that gives us. F at 1, negative 1. Well, we'll get 1 minus a negative 1, which will be 2, comma, now 1 plus, and that will be negative 1 minus a 1. So the 1 minus the 1 will cancel. Let me just write it out. All right, it'll be 1 minus 1 minus 1, it looks like. So it'll be 2, negative 1. All right, so we go out 2, then down 1. So something like this. Okay, so as you can probably see, this isn't the most streamlined way to do this. However, if you ever want to just get a gist of what a vector field looks like, this is the way to do it. What we tend to do instead is actually use software to help us graph. So let me show you some vector fields through graphing software. All right, so here's some I've put together ahead of time. Here's the vector field negative yx, and here these are the same graph except I use more grid points in this one on the right than I did here on the left, and on this one on the right I actually scaled the length of all the vectors down, and that tends to be what we end up doing so that we can get a look at what they're doing versus eventually these would all be off the whole graph. But you notice this is just the negative of that other one we looked at, which was y negative x, and we see that this field is revolving in the positive direction around the origin. Now, I think in this graph we get a good sense of what a vector field does. It represents a bunch of forces acting together in a system. So you can think of this as the flow of water or the flow of wind. And what you could see is if you dropped, say, an object here, that it would get carried along. So if you dropped, say, a rubber ducky here, it would start spinning around the origin based on the forces that we have here. Okay, here's another field. The vector field 1 comma x minus y, and again, the only difference is the number of grid points, and the more grid points I have, the smaller I make the scale, just so it, we can actually see what's going on. And as you can see, if I were to drop any object around here, it looks like all the vectors start pushing us along this way. Okay. Now this vector field here just shows that we've actually seen this before. The gradient is a vector field, right? If I have the function f of xy equals x squared plus y squared, the gradient of that is 2x comma 2y. This is something we've already seen before. And so here I have graphed a couple of level curves of x squared plus y squared, so that's a paraboloid. So all of the level curves are circles, and we see that here the arrows are the vector field itself, 2x, 2y, and we can see that's essentially that explosion field that we looked at originally, just times 2 instead of just xy. And we can see here that, yeah, those vectors there, that's the gradient. So we've actually already been looking at vector fields, we just didn't realize it yet, that the gradient is a vector field, okay? And that's actually going to come into play a bit later, but this isn't actually anything brand new. It's just this is our first time looking at it in a more formal context. Okay. Now, here's an example of some 3D vectors, or vector fields. Okay, these are a lot harder to graph by hand. In fact, I definitely wouldn't recommend it. But we see here we have the vector field XYZ. That's a nice explosion vector field, all the vectors exploding away from the origin here. Here's the vector field negative y comma x comma z fourths. So as you can see, kind of looks like we have a rotation going on, at least in the x and y coordinates. So it looks like we have some sort of spinning guy here. Here's the field negative z0x, and we can see it sort of revolving around, I guess, the y-axis or something like that. And then I kind of like this one. 0, comma, e to the x, comma, 0. All the vectors are pointing off in this direction, and they just get faster and faster as we push this way. So it's sort of like we start slowly and shoot off, right? So if we were to drop like a balloon into this wind tunnel, for example, it would shoot us across. All right, now this was a strange little vector field here that we looked at this point, but let's actually see what it looks like using another piece of graphing software. Okay, here we are. I've graphed this in software now, and it does look like along the diagonals, the 45-degree diagonals, it looks like all those vectors are the same along the diagonals, but they're pointing, here they're pointing, say, straight up. Here it looks like they're pointing straight over, and then along here, over here, we see they're pointing down to the southeast, and here to the northwest. Okay, and it's along here where they start to swap. All right, just to put it written out, what I mentioned before is that practically speaking, vector fields represent a collection of forces acting together in a system. So you can think of it as the velocity of water. So a velocity of a current, right? So you can think of, say, here's the water, and it's, you know, pushing at different velocities at different points in the river. So if we're a boat and we want to move across here, at each different point along our path, we're going to have a different force that the current is applying on us. So with the introduction of vector fields here, we are actually creating a system or a way to talk about way more realistic problems, because instead of some constant force acting on our boat as we travel along, we can have a different force at every point along its path, and we can model how much work would be required or how much force is happening along this path completely. Okay, it can also give you a sense of like motion, because based on the field itself, and if you've taken differential equations already, you'll recognize this in slope fields more than likely. But say if this was our vector field and this was our stream, let's say, and I just dropped a little rubber ducky here, it seems like we could use this representation here to describe how this rubber ducky would travel if it wasn't applying any force itself. Like if you just dropped it in and let the stream carry it along, that's also what a vector field is representing for us. Okay, so ultimately that's all there is to really talk about in this particular lesson. There isn't much to this very first lesson on vector fields. It's really just an introduction. In the next lecture, what we're going to look at is this right here. Okay, we're traveling a path through this vector field, and that vector field is applying force on us as we travel. So then the question is, okay, well, how much work is being applied? How much work does it take to move, say, the boat from here to here? Or that's just a quick little example, but that's what we're going to be looking at in the next video. Okay, so I will just leave it there, and I will catch you all in the next.